Okay, thank you. So in this lecture, I will give some background on two topics which are closely related, algebraic groups and automorphism groups. Okay, and this will be largely independent of lecture 1. Sorry. Well, things will come together at the final lectures on Friday. This will be Weil's regularization theorem. Well, in a other general setting, and in the final lecture, I will add some words which were put in green in this theorem with this projective variety. So maybe you remember in this theorem we had some new variety where some original algebraic group became an of rational transformation became a group of automorphisms. And I will try to show that you can take this variety to be projective. And this will take more than 1 hour and some cheating, but that's how it is. So this is a plan. Now you will find some notes of these lectures. You just search for my name. Well, okay. And then note de cours, French words, and then at the very bottom of some page, you find these notes. And I will really use these notes for certain proofs, because I think by maybe lack of time, I will concentrate on statements and examples and not give too many proofs. Okay. Anyway, what I will start with is pretty standard. These are the first things one does when one considers algebraic groups. So let me begin with this. So, as in the first lecture, I will work over algebraically closed fields. And then I'll define an algebraic group. G, this is just a variety with an additional group structure which is compatible with the variety structure. Equipped with morphisms. Well, there will be a multiplication, an inverse map, and a neutral element. And all of these morphisms and data should satisfy the group actions. Okay, so that's a very simple and basic definition. Let me give you a list of examples. Some of them occurred in earlier talks, but I just want to review them. Well, the first one is probably the additive group. This is a kind of official notation in this topic for this group. this is the variety. This is the affine line with m addition. E I of x is minus x, and E is 0. Okay, so that's some small example. Another one is multiplicative group, which also occurred in earlier talks. You just take the affine line minus the origin with multiplication. And of course, neutral element is 1. Okay, so these are very standard examples. The next one is equally standard. You take G to be GLN, general linear group. Well, you know that this sits in the space of matrices, which is an affine space of dimension n square, number of matrix coefficients, and this is the non-zero locus of the determinant. So it's a principal open affine subspace of this matrix. So it's an affine variety, and the matrix multiplication is polynomial in the matrix coefficients, of course. And the inverse of the matrix, you have to think a little bit. You just take the matrix of cofactors, whatever it is. These are polynomials in the matrix coefficient, and divide by the determinant. And since we are in the non-zero locus of the determinant, we can do that. And so what you get is a fine algebraic group. Okay. Well, there are some other examples which occurred earlier. Yes? Why? Because it's a principal open subset of the space of matrices, so it's an affine variety. Okay. These ones are more or less obviously affine. This one also, but a little bit less obviously, right? Okay. Well, the next example, this was PGLN, which also occurred in earlier talks. Well, as a group, it's defined as a quotient of GLN by the scalar matrices, which form a sub GM times identity matrix. So it's a quotient of this GLN. It's not completely obviously algebraic group, but you can see this if you think of this as automorphisms of the algebra of matrices. You look at the matrices as algebra for the addition and multiplication. Maybe I'll close this door. Sorry. And you let GLN act on these matrices by conjugation. And then the kernel of this action is exactly the scalar matrices. So you just get a faithful action of the quotient. And the theorem of maybe Skolem-Noether says you get all automorphisms in this way. And this is clearly an algebraic group because it's contained in this UGLN square, the group of all automorphisms, defined by a closed condition to preserve the multiplication. Okay. So that's one possible reason. We will see a bit later that quotients exist. But you can do this at this stage. There were some additional groups which also occurred, elliptic curves. And by this, I mean a curve of genus 0 equipped with an origin. So C, yes, smooth projective curve. G of C is 0. And this, sorry, well, thank you. Why should I? And this is a k-rational point. And there is a unique group law which has this as an origin and which is commutative, and this is an algebraic group law. Okay, and well, more generally, you have these abelian varieties, which also occur in earlier talks. Let me put them on the list. By definition, this will be the connected and complete algebraic groups. These are some kind of minimal definition for this, and one shows that this implies that they are projective as a variety. And they are also a commutative group. The group law is automatically commutative, and again, uniquely determined by the origin. But that's another matter. So over C, you recover the maybe more classical presentation as a quotient of some Cn by some lattice, because the universal covering of a commutative group is C to some power. Okay. So these are lists. This is a big list of examples. Well, you still have two types of groups in this list. You have the linear algebraic groups. So maybe I'll give the definition. An algebraic group is linear if it is isomorphic to a closed subgroup of GLN. Closed group of some GLN. That's a usual definition. So you see that linear implies affine, because it's closed in an affine group. Actually, you have equivalence. This is not too hard to prove, but I won't do it here. And in this list, you see, well, of course, 3, 4 are linear. And 5, 6 are not, because you see there are projective varieties. All the regular functions are constant on such objects. Okay, we will see later that every algebraic group can be obtained from linear groups and abelian varieties in a kind of precise way. Maybe I don't mention it right now. Well, I should mention some important facts, that you also have some the notion of group schemes. Where you just replace variety by scheme, and you have the same formal definition. And there is an alternative notion of algebraic group, which should be a group scheme of finite type. Maybe I'll put it in quotation marks to say that it's a generalization. And of course, it contains the ones over there. And actually, this is the same in characteristic 0. Same notion by a theorem of Cartier. Which says precisely that every group scheme of finite type is reduced. So it's a variety. Okay, you should prove that it's separated, but it's completely trivial. So I'll leave you as an exercise. And if in positive characteristic, it's completely different. So you get more. Many more algebraic groups in this sense. For example, you take the pth power map or its powers, GA to GA, which sends x to some power of p. Okay. This is additive in positive characteristics, so it's a group homomorphism, and you take its kernel. I should give a name of this map. This map has an official name. This is an n-Frobenius morphism. And it's called alpha e to the n. This is a schematic kernel. This is a schematic fiber at 0. So you see it's a functor which associates with any algebra the set of elements of p to the nth power 0 in this algebra, equipped with addition. And you see if the algebra has nilpotent elements, you get points. And this is certainly not reduced, right? And what's also remarkable is if you look at this family of subgroups for all n, you get something which is schematically dense in the affine line. This means the closest, the smallest subscheme, which is closed and contains them all, is the whole line. Because you have maybe not all the infinitesimal neighborhoods of the origin, but a final system of neighborhoods. Okay? Or in more concrete terms, if you have a polynomial which vanishes at the order bigger than p to the n for all n, it's 0, right? So you see this very smooth and natural object is approximated by this infinitesimal objects. Well, yes? Okay, there are two kinds of answers. The first one is for any group scheme, the module of differentials is free by just this translation argument. Now in characteristic 0, there is a theorem of Grothendieck which says over a field of characteristic 0, some scheme, finite type with free omega 1 is reduced, very smooth at roots. And the proof is just differential calculus. You have this module of differentials, take a basis, take a dual basis of derivations, use this dual basis to build a power series expansion of functions by Taylor's expansion. And in Taylor's expansion, you have to put factorials, and that's why characteristic 0 comes in. And that's a very neat proof that you find in the book of Mumford, Abelian Varieties. This book has a section of group schemes which contains many nice basic facts, and including a short proof of this. I will give a dirty proof for affine group schemes in this lecture. But it's a bad trick. Okay, anyway. Yes? It's not reduced. Certainly, it's even finite. I mean, if you look at the coordinate ring of this gadget, it's a quotient of the polynomial ring in one variable by the x to the p to the n. So that's a defining equation. So this is a finite dimensional vector space, and you get a finite group scheme. It's just non-reduced. It has a unique point, which is its neutral element. So from now on, we will assume characteristic 0. Certainly to avoid technicalities. Things can be restored in positive characteristics, but with more work. So now I will, well, if there are any further questions at this point. Okay, so let me give you some first kind of structure results on group schemes, on algebraic groups, sorry. Well, anyway, so the neutral component is a very useful result to start with. So you consider an algebraic group. Then there is this special point. And I consider the connected component of this group, which contains E. Okay, just by definition a closed subvariety, and then the statement is that G0 is a normal subgroup of G, and smooth irreducible variety. That's the first thing, and then the quotient G mod G0. This is a finite group. And the cosets modulo these groups. These are the connected components. Okay. Well, the proof is really an exercise. I will not give it in the notes. You can cook up your own proof very easily. What I want to stress is this gives you some exact sequence. You have this G0 in G, and the quotient I will write as pi 0 of G, as a group of connected components. This should be finite, should be connected. Okay. You see, for example, that every algebraic group is smooth, because it's a disjoint union of translates of this smooth thing. This is very easy to see directly, because it has a smooth point somewhere, and you can translate it everywhere by multiplication. So that's see? Yes. Yes, and you're right, but the existence of quotients is not an immediate fact. Maybe I'll come to this later, because you see, even quotients by finite groups requires a little bit of effort, but quotient by a subgroup is a non-trivial fact. But you define it explicitly. You have an explicit construction. And you're perfectly correct to point this out. But again, constructing quotient is not easy. If you have a candidate, it's easy to prove that it's quotient. Okay? Then you just find it. Well, maybe where's the example? All the examples that I'm erasing are connected, so it's not too interesting from this viewpoint. Well, you will see examples of disconnected groups. Let me give you a short one. Take the orthogonal group. This will be the subgroup of GLN, which stabilizes a non-degenerate quadratic form. Then what you get is the connected component of the identity is a special orthogonal group, the kernel of the determinant. And the group of components is and the sequence I wrote is just this one. But big deal. You also see that in characteristic 2 there may be problems. But I'm definitely in characteristic 0. So. Okay, so that was maybe some kind of warm-up. Then I should also define algebraic group actions. This will be the next definition. So action group. E on the E. X. What you expect from the definition of algebraic group, you give yourself the action morphism. Is a morphism of varieties from the product of this. Hence, any pair is some thing I will denote G dot X for simplicity, which satisfies the properties of the action. Yes? I think for this one, this is because if you take the determinant of an orthogonal matrix, you get only plus or minus 1. And so you don't have to worry whether you have roots of unities. Okay. This is rather when you go compare, I don't know, SLN and PSLN, then UN comes in. So it's a different direction, right? Is this? Well, of course, this axiom is as follows. The identity element acts by the identity, and G dot H dot for all points. I'll write this explicitly because in the near future, we will generalize this to rational actions, and this will be definitely more tricky. I mean, it's not enough to put dotted arrows in the definition, and you will see you need a little additional input. But for now, we are working with this. Well, when you have an action, you have the orbit. E dot X. This is the image of the morphism given by acting on X. I should state some basic properties of orbits, proposition, even if this is also very basic. So every orbit G dot X, my notation for orbit, is locally closed. Smooth. Three-dimensional dimension G index X is a stabilizer. Well, this is called isotropic group. Stabilizer. That's the first point. The second point is if you look at the closure of the orbit and remove the orbit, is a kind of boundary what you add when you go to the closure. This is a union of orbits of smaller dimension. The boundary has smaller dimension. This is perfectly clear if G is connected, because you work in an irreducible variety and you remove an open set. In general, it's just an exercise, and then closed orbits exist. So these are the main the observations you need to work with these effects. Let me comment on this statement. Again, you find the proof in at the very beginning of any textbook on algebraic groups, also in the notes. And the explanation for this statement is just you consider the image of a morphism like this. A priori, the image of a morphism is just a constructible set in algebraic geometry, right? And so you say, well, you should know that a constructible set contains a dense open subset of its closure. The Weil's theorem. And also an orbit is homogeneous. All the points are the same. So open its closure by moving this dense open set everywhere. Smooth for the same reason. And the statement of the dimension is just a classical result on the dimension of fibers. The fibers of this orbit map, well, there is a special fiber at the identity element, which is just this group Gx, and the other fibers are translates. So they have the same dimension. So if this is too quick, you just go over the proof quietly, and you get the same because not a big, not a deep statement. It's just useful. Okay, it has a very important corollary that I state here. If you consider a homomorphism of algebraic groups, this is just a morphism of varieties, which is compatible with the multiplication, and then its image is closed. And you have the same dimension as in linear algebra. Dimension of G minus dimension of the kernel. Okay. Again, it's just like linear algebra. And the proof is one line. Let me give it. You let G act on H for this homomorphism. Okay. And multiplication. And then you see the orbits are cosets. All the orbits are closed. This have the same dimension, which is given by this. Well, so this is really an observation, but it's extremely useful. For example, we give just two of them. First of all, we had this homomorphism from GLN to GLN n square, which is GL of the matrices, which was conjugation. So G mapped to the inner automorphism of G. Wow. Okay. So its kernel was a multiplicative group, and we see from this corollary that its image is closed. And this gives another proof that PGLN is closed. You don't need to know the Colem-Noether theorem. Well, that's the first remark. Maybe the second observation is if you have a linear algebraic group and an abelian variety, then you have no morphism, no non-constant morphisms in both directions. Only constant morphism because you see from this direction the image should be affine. Fine and irreducible, but in the projective variety there is no room for that. And in the other direction, same. You have a projective subvariety. So that's something to keep in mind. Now, I will say one word about homogeneous varieties. Because they will play a key role in the proof of this Weil theorem. This is just G variety, means variety where by group G acts, homogeneous. The G action is transitive. And this means that there is a unique orbit, then name it X. X is isomorphic to the homogeneous space G mod H, where H is any isotope. Okay. So that's just a definition. Well, you saw in Evgeny's lectures some examples of homogeneous varieties which had no point, no rational point over a non-closed field. And they will occur also finally, but at this time we work over an algebraically closed field, so we are allowed to. Okay. Well, there is a theorem of Chevalet, which says that you can realize every G mod H in sense. So if you have a linear algebraic group and H a closed subgroup, then H is the stabilizer of something or some X in a projective, in a G variety of a very special type. This will be the projectivization of a representation of G. Representation in the sense of algebraic groups. You have a homomorphism of algebraic groups from G to GLV. I should add the finite dimensional. Sorry for the... And so this maybe partially answers your question, because you can identify this homogeneous space exists. You just decide that it's the orbit in your V, and you get that it. Okay, and that's actually the proof of existence of homogeneous space in this setting, linear algebraic groups. Maybe I'll derive Cartier's theorem in a special case from this. Yes? Yes? Well, first of all, I mean that this quotient exists in the sense of, I don't know, for example, categorical quotients. And then you get an isomorphism by sending the coset model. That means that there exists a point in X with stabilizer exactly H. The orbit of this point. Okay. Well, it's a bit compact, but it's understandable. Well, I wanted to mention this dotted proof of this theorem of Cartier. So every linear algebraic group is smooth. Every affine scheme. And the proof is really observation, because you consider your group scheme. Fine being the same as linear, and this part is easy. You can put it in some GLN as a closed subgroup scheme. And then you consider the quotient map. This exists because this Chevalet theorem is really a construction which works for any subgroup scheme. It's obtained by clever manipulations using representation theory which work for group schemes. So this makes sense. And now this is smooth. And you just use generic smoothness. Every dominant here, the surjective morphism from a smooth variety, has smooth fibers over some open subsets. The fibers are all isomorphic to G. Well, this is just that's the trick. And again, the general proof is much more interesting. Anyway, so that's some very small crash course on algebraic groups. We will see later if we need more. What I want to do now is explain or present some functorial properties of group actions. So this will really be used at every step of this proof of Weil's regularization theorem and its refined versions. What I mean by functorial will be clear from the context. Well, the first one is the following. You have a G action on a variety. And, well, maybe I assume the variety is reducible. And you have the normalization. It will be the normalization map. Okay. And then the claim is the action lifts to a unique G action on X prime. And, well, this looks completely obvious because you can lift every automorphism to the normalization. The only point is you have to lift with a morphism of varieties. So you have to be a little bit more careful with a global statement. So let me give a proof for G connected. And, the general case is obtained from this. Well, okay, you have you consider the product G times X prime. So this is a product of normal variety with a smooth one. And so it's normal. If you don't believe me, you work this out by Serre's criterion for normality. That's the only proof I know. Okay. That's probably the official proof. Maybe I'll put exercise. And then you have a map from this normal variety to X, which just comes from the action map. you call? Okay. And you have the normalization. And well, also this variety is also irreducible, so there is a universal property of the normalization which tells you this lift uniquely. Okay. This lift I will write as A prime. And by definition, it's a lift of the action. And you see just a morphism. But over the set of normal points of X, you do nothing. So you get the same action. And then it's an action by just taking closures, right? It's an action of a dense open subset. It's an action everywhere. And that's a proof. Oh, well, it doesn't, not a big deal, but it's a very useful trick. There is a similar trick with resolution of singularities, but it's more just more advanced setting. Because I use the fact that this is an irreducible variety. It's not really essential, yes. I could, anyway, the proof is separating everything into components and looking at each component. So I didn't want to get involved in this. It's optional. So this was for normalization. For canonical desingularization, which I briefly introduced, but at some point I messed it up, so let me correct. So you have a variety, and this canonical resolution constructs, maybe I'll denote by x tilde, and maybe phi. So this is given. So this should be smooth. Phi should be birational and projective. This defines for you what desingularization is, and where you require, in addition, that there is a process of constructing X tilde which commutes with smooth pullbacks. And this means the following. You start with your X. You build its canonical desingularization. There is a procedure with blowing up specified centers. And then you have here a smooth morphism. And then you have its canonical desingularization here, note by center. And the statement is that y tilde is canonically obtained by this pullback. Well, if you pull back a smooth morphism, you get a smooth morphism here, so you get another resolution of singularities. And the statements, the property is that it's exactly the same. And in particular, what you can do, well, the statement, the proposition, which can be found in Collard's book. every algebraic group action on X lifts uniquely to this X tilde. Okay. The proof is very well explained in Collard's book. It's really a formal consequence of this commuting with smooth morphisms and well, some arguments. So let me sketch how this works, because it's essentially the same ideas here. You just consider the action morphism. Okay. This is part what you have. So, and the statement is that this morphism is smooth. Maybe it's not completely obvious, but it's isomorphic to the projection. So you just do this. X. This is an isomorphism, and this is a projection with smooth factor, so it's smooth. So you see this map is smooth, and you can apply this Collard commutativity of the diagrams, and the fiber product is this. And so you get a morphism like this. That's your lift. And when you look at things carefully, you see this is the same action on the locus where this map is an isomorphism, so it's an action. Again, details in Collard's book. Well, there is another very useful construction that I should mention. This is a blow-up. So the data are as follows. You have a G variety and a G stable, maybe a subvariety closed. Okay. G stable means that G, Y, and then you can construct the blow-up of this subvariety. And the statement is again that G action lifts uniquely to these blow-ups. The proof is the same kind of abstract nonsense. This time you use the fact that blow-up commutes with flat pullbacks. Sorry, this is French mathematics, but blow-up commutes with flat pullbacks by the very definition of blow-ups. For example, in Hartshorne's book, we use the definition with the proj. Okay, so that was a sequence of results which tell you how to lift actions. And there is one result I will use which does the opposite, which pushes down actions or descends action. Yes? The smooth morphism well, it's a flat morphism. Is it okay? With smooth fibers. Smooth schematic fibers. Okay? And another way to saying this is flat morphism and the usual exact sequence of tangent sheaves is really exact, if you would like. So the differential map is surjective. Okay? So that's the most concrete definition, which is, I guess, perfectly correct in this precise setting. In general, you need some additional words like locally of finite presentation. Sorry. Sorry. You can live with this one. Okay. So what I want to mention next is anyway very important construction is in birational geometry. Important notion is this notion of contractions. Well, this is another abstract definition, but it's really a central gadget in a topic. So you have a formal definition. Morphism. Is a contraction if F is proper and at the level of structure sheaves you get an isomorphism. So this condition means for any open subset you get a map which is just pulled back by F. Okay, so that's a definition. And the main examples some examples. The first one you can find is a projection. Take y times z projection is a contraction. Say z is complete to get a proper morphism and irreducible. That's a standard example of contraction. Maybe a more interesting one is you take a proper birational to a normal variety, for example, smooth. Because this condition here is just Zariski's main theorem, which is a theorem, okay? But still, that's, so you see, most morphisms in birational geometry tend to be contractions. Well, maybe more. Now what I want to state is known as Blanchard's lemma. The descent result for contraction. So you have such a contraction. And assume that you have an action of a group on the source, not this time, not on the target. And this group should be connected. Then the statement is there is a unique action on Y such that F is equivalent. In terms of diagrams, you have something like this. You start with your action. You have your morphism. Here you have another morphism, which is entity F. And then there should exist a unique arrow here. Makes the diagram commute. I won't use a dashed arrow. Okay. And here the connected assumption is very useful by a standard example that you saw this morning. You consider a Z mod 2 acts on maybe P1 times P1 by changing the factors, right? And if you consider any projection, the second one, it's not equivariant for any kind of action. You cannot descend the action. So for finite groups, that doesn't work. But the main thing is it works for connected ones. Yes, actually, corollary of this is a connected automorphism group of a product is the product of connected automorphisms. So I'll come to that in a well, but I realize I'm very slowly going through many generalities, and well, I still need some other ones. So I'll skip the proof entirely. It's really an advanced exercise in algebraic geometry, and you can use it as a problem on a course on scheme theory, for example. Just cut it into pieces, and each piece is not really complicated. Well, I will now discuss automorphism groups. Projective varieties. With the idea that they should be really close to algebraic groups. And this idea is correct, but to some extent. You have to be a bit careful. And I'll start with examples to illustrate this. First of all, the most important example is automorphism group of Pn. I just consider this as an abstract group for the moment. There is no additional structure. Then you know it's PGLN. 1. And to emphasize it's an abstract group, I just put a point. Well, maybe a more surprising example, if you look carefully, take an abelian variety. Then you see as an origin. Well, it has a group structure, so it has translations. And translations give you lots of automorphisms. I will denote just by X the group of translations. So to be completely fussy, I should put X of K. Anyway, let me put this. Okay, and now there are additional automorphisms that you know very well, for example, -1, or automorphism of the group. And you have another subgroup, which is the automorphism group which fixes the origin. I'll denote it like this. And it's a known fact on abelian varieties called rigidity, which says this is automorphism as group. And okay, given any automorphism, you can correct it by a translation so that it fixes the origin, right? Just do like affine transformations. And this gives you actually the statement that actually this automorphism of groups normalizes the group of translation, and the full group is a semi-direct product. Okay. So that's not hard to prove once you know that odd 0 is a odd group. And what is known in addition is this group is finitely generated. And possibly infinite. Well, you don't see this if you take for x an elliptic curve. Then you have seen, I guess, that odd x0 is cyclic of order 2, 4, or 6. It's a small group. It always contains -1, so it's of even order. And sometimes you have an additional symmetry. But if you take, for x, the product of two elliptic curves, this is an abelian surface. Then this odd x0 contains some group like GL2 of Z, right? Because you can act on your product of elliptic curves by linear transformation with integer coefficients, right? Linear combinations with integer coefficients. So you get this infinite group, and this is actually the full automorphism group if E has no complex multiplication. Meaning that the only endomorphisms of E as a group are the multiplication maps by integers. So, well, as you see, this group is can be infinite. So you cannot expect, well, from this, the guess would be that you would have an exact sequence like this. This would be X. Then you would have an algebraic structure here, and then this group of components to follow the earlier notation should be this one. Okay, and it's possibly infinite, so this is not algebraic, but very close to this. So let me state a general result, which is hopefully motivated by this example. Well, I'm guessing some factor of algebraic group or related object on OTX, not only an abstract group. So if it has such a structure, its connected part should be the translations, and its group of connected components should be this one. Okay, and that's what happens. In fact, but you have to define the structure correctly. For this, in the notion, adapted notion is a notion of family of automorphisms. Would be no surprise for you if you saw some examples of moduli spaces where you define families and show that they are parameterized by some moduli space. So you fix a variety. Family morphisms X parameterized by some objects. S will be here. You can take the variety, and this will be correct. You can think of it as a scheme. Let me define it formally. This will be a map, morphism, F from I choose this for reason, such that map is an automorphism of this product variety. So what you define in this way is what's noted some morphism of S times X as an S. So these are the families from this group. And there is a kind of obvious operation of families which is pullback. By morphism U. Another variety or scheme. This is just family over E times X is given by composition with this morphism. So once you have defined this, you have a notion of universal family. Is one from which every other can be obtained by a unique pullback, like in all universal problems. And then the guess, sorry, another guess, should be that this should be this one. You have a candidate for this, which is just the action of the automorphism group on the variety. Okay? And the theorem says the guess is correct if X is projective. This is the action. Sorry? Up to now, everything is formal. No. Well, this will be part of the statement. So let me put the statement and then discuss it, because you will indeed enlarge the notion of algebraic group. So, yes? Yes? No, but the statement will say that there is a unique. No. Yes, yes, that's what I want to arrive at. So if X is projective, unique structure. Well, here you can put what you say, scheme locally of finite type. There is another option, which is to define locally algebraic group, which I will do next. Note X. That this action map here is a morphism and is the universal family. Okay, so I think this notion is self-contained but a little bit abstract. This requires a definition. So let me give it next. You just think of an algebraic group with infinitely many components. So this will be a topological group. Yes. So let's start with just a topological group, G, which will be the disjoint union of pieces indexed by anything. Gi is an irreducible variety. This will be the connected components, and you require that the multiplication map sends Gi times Gj to some G k of Ij. This should be a morphism. Because this makes sense, because all pieces of this are varieties. And likewise for the inverse map. Put it next. Would be also a morphism. Okay, just think of algebraic group with infinitely many components. And, for example, any discrete group is locally algebraic in this sense. You just think of Gi as points. So yes, because group scheme locally of finite type can be something like infinite chain of curves connected, and this doesn't occur in as a group, because locally a group cannot have points like that. Then it's this one. Yes, yes. Fine. Sorry, I didn't understand the question. The notion is more general, but it specializes to this one. Maybe this one is slightly more concrete. Okay. So, okay, so I'll really work with this one. And the consequence of this is that the connected component of the identity is a honest connected algebraic group. This defines old 0 of X connected algebra. And the quotient by this is again a normal subgroup, and the quotient is discrete in the group of components. So that's the end of the theorem. Well, I'm very late, and it's already a big pile of abstract nonsense, so I won't give a proof. I would like to explain in the remaining 2 minutes how you can use it to get another understanding of the automorphism group of Hilbert surfaces. And you see they come with a map to P1, which is the ruling, which is a contraction, okay? Because it's a P1 bundle, so the direct image of the structure. If right. So you can apply Blanchard's lemma, and then you work with this old 0 of Fn. Okay, because in Blanchard's lemma you have to assume the group connected. I'm not sure that the group is connected. So if we land into old 0 of Pn, P1, right? Is PGL2, no problem with this. And there is a kernel. And the first observation, which occurred in Jeremy's talk, is that this map is surjective. Actually, there is an action of GL2 on this, which lifts this action. You had some, actually in the talk of Jeremy, you have an action of GL2 on mu n, so you have a part like this, and this was onto. Okay, so the main task is to understand this kernel. And for this, we use some geometry. You have this map. Fibers P1, and it has 2 sections. It has many sections, but it has a canonical one. It was S. Here I assume n bigger than 1. So you have this section. And this is a section of self-intersection minus n, and it's the only negative section. So it's stable by any automorphism. And now this kernel acts on this picture by acting on each projective line, because it acts trivially on the base, which is here. And on each of this line, it fixes a point. Which we may think of the point at infinity of this projective line. So it acts by affine transformations, which depend on the base point. And the statement is that this K is the semi-direct product of GM, which would be the multiplicative part of this transformation, and some additive group, which was denoted by K of X, Y, Was it x0, x1? You correct me if I'm wrong. Index n. So this is an additive group, and this would be the group of translations on each fiber. And these translations are just the sections of the O of n that use definition of this Fn. And actually, this picture can be recovered if you use another section, because you had another one running out of chalk. You have two disjoint sections, because this corresponds to the fact that this vector bundle that you use is split. You have one section corresponding to one factor, another one corresponding to another factor, and they are disjoint because you have a direct sum. So on each line, if you choose from this decomposition, you get a second point. And now this GM fixes these 2 points. It acts by a scalar, and this scalar is constant on fibers, but the translation part can move. And that's some non-trivial fact, but it's related to these sections of this O of n translated on fibers. No, it's just fixed by this GM. So you see, think of the group of affine transformations of the affine line. You don't have any origin. You have the GM somewhere. To see this GM, you have to fix the origin. And that's what I'm doing here. So maybe it's a good place to stop, because thank you. Just,
so if you have X affine, do you have a similar kind of statement for auth X? Or?
First of all, auth X is just an in group, not an algebraic group, kind of increasing union of affine. I'm not sure. Not an expert. Maybe Michael. The question is, if you take an affine variety, take its automorphism group as an in group, does it have a well-defined connected part and group of components? But the discrete part is really discrete, or it's just the non-connected part is really discrete, or it's just the group of components? Is it still discrete, or it's just some strange object? Okay. Okay, so. Yes. Yes. This index set is countable, yes. For projective varieties, yes. Oh, no. Yes. So this one is discrete because you see this by constructing really this X in terms of graphs. Well, okay, the idea of the construction of this X is to associate to each automorphism is graph as a subvariety of X times X, and to consider a parameter space for graph like Hilbert scheme or Chow variety. And each of these parameter spaces has only countably many components, even by fixing the Hilbert polynomial or the degree. And then you see you have countably many pieces, but you don't control them. Yes? I'm sure I wanted to write it, but I don't remember. Well, this is also optional. Mm-hmm. Yes. It's in particular a topological group. It's not separated in the usual sense of group, but it has a Zariski topology. I'm thinking of a scheme as a topological space together with a structure sheaf. And I'm starting with the data of the topological space and building some kind of structure sheaf out of it, in addition, sorry. Okay? But that's, if you're used to separated topological groups, then certainly.
Zariski topology.
Yes. Well, maybe it's not a happy world. You can live with that. Sorry. It's countable. But you had an objection from Stefan. So. Thank you.